infinity is here. We have done it here. Where is that lemma? In our lemma, we have done it in our lemma. Okay, so let me. So that lemma is this. For any reflex relation S on X, the relation S infinity defined by star is transitive relation. So that means S infinity is also transitive. So which means E is transitive. So E is reflexive. So therefore what's E? E is reflexive, symmetric and transitive. So therefore E, which is equal to R union R inverse union Ix whole infinity is what? Is an equivalence relation. Is an equivalence relation containing R. Is an equivalence relation containing R. But we need to show that this is equal to RE. RE means the smallest equivalence relation containing R. So let's take any relation, any equivalence relation containing R, and we show that this relation is subset of that 1. Okay. So let sigma be any equivalence relation containing R, that is R is subset of sigma. So this implies R inverse is subset of sigma inverse, but sigma inverse is same as sigma because sigma is an equivalence relation, so it's symmetric. Sigma inverse is same as sigma. So and Ix is also subset of sigma. So R inverse Ix, they are all subset of sigma, which means that R union R inverse union Ix is subset of sigma. So which implies that our S is R union. That's our notation. What's S? S is this R union R inverse union Ix. It's our S. So that means S is subset of rho, which implies S square subset of rho square. But rho square is same as rho. So let rho be any equivalence relation containing R. Then R is subset of rho. R inverse subset of rho inverse, which is equal to rho. Ix subset of rho because rho is reflexive relation. So that means R union R inverse union Ix subset of rho. So which implies this S is subset of rho. So but then S square will be subset of rho square, and rho is transitive, therefore rho square is same as rho. So in general we have Sn subset of rho for all n greater or equal to 1. Okay, so our Sn. So you had this Sn subset of rho for all n greater or equal to 1. So which implies union Sn n runs from 1 to infinity subset of rho. So that means S infinity is subset of rho, which implies E is subset of rho. But what is this? E is actually R union R inverse union Ix whole infinity subset of rho. So that means any equivalence relation rho containing R contains this relation. So which means this one, it is already proved that this relation is an equivalence relation. Now we have proved that. Now we proved that, and for any equivalence relation rho containing that relation R, then this one is contained in rho. So which implies R union R inverse union Ix is the power infinity, is the smallest equivalence relation containing R. So which implies RE is equal to R union R inverse union Ix power infinity. So that proves this proposition. So next, now as already I mentioned that we try to impose certain conditions on equivalence relation on SME group S, so that the quotient S over sigma S over that equivalence relation will become a semigroup, so that we can define operation on S over sigma. So So that concept is actually that's actually congruence. So before defining congruence, let me first write here one more proposition. Then we'll go for this congruence relation. If R is an equivalence relation, if R is any relation, not equivalence, if R is any relation, if R is any relation on X any set, then so that's actually the disc. Then Xi belongs to Re if and only if X इक्वल टू वाई, इधर x इक्वल टू वाई आर, या तो ये इक्वल हो गई x इक्वल टू आई, आर फॉर सम m, और फॉर सम n greater or equal to 1 natural number, there is a sequence of transitions. There is a sequence of transitions. Okay, there is a sequence of transitions. What is that? X equal to x1 transition. Let me denote this arrow. We call it a transition. Let's say right here is not x z1, z2 transition. Say z3 transition. Continue this transition, and we have then we have at n stage zn, which is equal to y. That transition means that in which this transition means that Zi or Zi plus 1, they belong to R union R inverse. Either Zi plus 1 belongs to R, or Zi plus 1 belongs to R inverse. Okay. So that means whenever Xi is in Re, then either X equal to Y or X and Y, they are connected by these transitions. But where Z1 comma Z2 transition means that Z1 comma Z2 belongs to R union R. So transition means this. It belongs to R union R inverse. This is the meaning of transition. Meaning of transition means Z1, Z2, it belongs to R union R inverse. Meaning of transition. Okay. So if Xi is in Re, then if X equal to Y, then we have nothing to prove. So we assume that X is not equal to Y. X is not equal to Y. And let's see this. So proof. If X equal to Y, then we are done. Then we are done. So assume X is not equal to Y, and X comma Y belongs to Re, means R union R inverse union Ix infinity. So infinity means it's actually union of Sn and runs from 1 to infinity. What is this? S is equal to R union R inverse union Ix. So this means this X comma Y, it belongs to Sn for some n. So that means X comma Y belongs to R union R inverse union Ix power n composition. This relation is composed n times. So n times means that there exists obviously Z1, Z2, so on, Zn, such that this X comma Z1 belongs to this, Z1 comma Z2 belongs to this. So let me write here say such that Z1 comma Z2 belongs to R union R inverse union Ix. So let's denote this Ix. Actually I can denote it by, if suppose there is an equality at certain stage, then we can remove that part. This is, and Z2 comma Z3, it belongs to R union R inverse, and so on, Z3 Z4 up to Zn minus 1 Zn. So what we have then, what we have, it's so we have this then Zi comma Zi plus 1, it belongs to R union R. So let me not write Ix here because I can remove that part. So we have done this. So let me write here X. Suppose X equal to Z1. I can take the first X equal to Z1. Then this is transition Z2, transition Z3, transition so on, transition Zn, and this one is equal to say Y. So there is a transition. And conversely, if there is transition like this, and conversely if it happens like this, then Z1 comma Z2 belong to this. They are all in this. So that means X comma Y belongs to. So in that case, Z1 comma Z2, or you can write in general Zi comma Zi plus 1. It belongs to them because Zi comma Zi plus 1 belongs to R union R inverse, so it means that it belongs to Re as well, because Re is equal to R union R inverse union Ix power infinity, and this relation is an equivalence relation, so which means that X comma Y belongs to Re. Okay. So Z1 is related to Z2, Z2 related so on. So that means Z1 is related to Zn then by transitive property. Okay? By transitive property. So this is it's very simple, this proposition. So that's actually the description of Re in terms of the relation R, where Re is the smallest equivalence relation containing R. Now next is the concept of concurrence. So concurrence is actually it's an equivalence relation with the it's a concurrence is defined on a semigroup, not on any set. So let S be a semigroup. Then a relation rho, which is a subset of S cross S, it's a relation on S. This relation is said to be a concurrence on S. If rho is an equivalence relation, first it should be an equivalence relation, and second rho is compatible. Rho is compatible with the binary operation, with the operation of S, because it's a semigroup, so there is a binary operation. First it should be equivalence, means that it has nothing with the binary operation on S, it's equivalence relation. That's simple. It's reflexive, symmetric, and transitive. But second property is important, that this relation has certain compatibility with its binary operation. By compatible, what we mean by compatible? By compatible, we mean that if x1 comma y1 belongs to rho, x2 comma y2 belongs to rho, then this should imply x1 x2 comma y1 y2 belongs to rho. So that's the compatibility. It's compatibility with its binary relation. Or we can say this, or this can be written as or we can define left compatible like this. We can define left compatibility. Left compatible. What's left compatible? We mean that left compatible by means x comma y1 belongs to rho. It implies that that x1s comma y1s, this should be also in rho for all s in S. x1 is also in S, y1 is also in S. But left we can multiply by any element on left side. So certain the pair belongs to rho. That's called left compatibility. Similarly, we have right compatibility. Right compatibility means whenever the pair x comma y1 belongs to rho, and if we multiply on left hand side by any element of S on left hand side, on right hand side the pair, resultant pair, say sx1 comma sy1, it should also in rho for all S in S. That's right compatibility. And we have proposition, a relation is left compatible and right compatible if and only if it is compatible. Compatible means that x1 y1 belongs to rho, x2 y2 belongs to rho, then this product should be in rho. This type of project x1 x2 y1 y2, okay, it's in rho. It means the compatibility, and this left compatible is this, right is this. And we show that the relation rho whether it's equivalence or not. But by compatible we mean this, by left compatible we mean this, and by right compatible we mean this. And by congruence we mean equivalence relation together with compatible. Equivalence plus compatible means congruence. So for compatibility we have following result. A relation is compatible if and only if it is both left as well as right compatible. So that's very simple. You can see its proof from the book at page number 23. That's very simple. I'm not going to discuss it here.